Well, it's just summation. Yep, summation, multiplication, but you have layers and layers of those. Yep. It is not complex when you look at one single neural network, but how you structure the neural network and how they interact with each other, that becomes complex. Hmm? Yep, yep. And also how you train it, that also is important. Yep. So all the LLMs and GPT technology is actually really complicated, takes a lot of work, to kind of train the models. Alrighty. So let's get back to this class. Okay, Canvas kind of messed up. It duplicated all my modules during the downtime. You guys won't see it because I hid all of those, so you cannot see those. So it's not going to be as confusing to you. All right. So what we'll do today is to continue our discussion with function calls in assembly language. We are done with calling and returning by itself, okay, which is this particular module. We definitely talked about stack operations. In fact, you did a lab on stack operations already. We were starting to get into the caller callee agreement, okay. What we have not really talked about yet is how we deal with parameters and also local variables and also return values. Okay, so we're going to have to hit on those topics today in a particular order. Okay, so we'll go ahead and talk about things that are, I'm going to say, without local variables, it's pretty hard to illustrate the other ones. So we're going to have to talk about local variables first. Okay. All right, so our current focus is local variables, and then we'll see, how long it takes, and then we'll determine what else we can talk about in today's lecture. All right, so we are going to take a look at, um, well, I guess we can look at online GDB first, and we'll write a few completely pointless and useless program, just so that we get the point across. Okay. So in main, we're going to say, okay, we have a local variable x. We'll even give it a value like 32. And then we're going to have another function here, okay, function f, which is a void function. It takes no parameters, and it has its own local variable x2. And this x is going to get a different value, let's say 42. And then main is going to call f at this point, and we'll see what happens, okay? So we already know that in regular C++ or C syntax, this is a useless program. Okay, it doesn't do a single thing. X is local to main, so main has its own local variable x, which is going to get the value of 32. When we call f from main, f is going to have its own local variable x, which is going to get a value of 42, but that 42 never interferes with this 32 because those two local variable x, they have different scopes for one, but they also have different storage. So they're completely independent. They just so happen to have the same name of x. Is that okay? So we can now go through this program if you want to, or if you say, okay, we kind of know what this program is not going to do anything useful, and then we can just skip it. All right, let's do it. The stack frame is going to be interesting because you can actually visualize that in GDB. So GDB has, okay, so let's do that, okay? Because if not for anything else, I can show you the tools that are available in GDB so that in your other classes, let's say 400 and 430, when you actually have to deal with larger and more complicated programs in C++, you will know that, oh, okay, I know there's a tool like this. I can actually go back and forth between quote unquote the frames. Okay, so let's do that. So let me first put a breakpoint on right about here, and then we're just going to debug the program, and then we'll go ahead and run the code. Okay, now we're on line 20. So on line 20, we say what is x? X is 32. We can also visualize it here. Eh, we kind of know that. It's no big deal. So now we single step into function f. So now you can see that there are two call stack entries here. Uh, Frame number 0 refers to the frame of the invocation of F. Frame number 1, which is one below the current frame, is the frame of main in execution. So when you ask what is the value of x after this point, so I have to single step one more time. So now that we are on line 14 and I ask what is x, the answer is, oh, it's 42 because we are looking at local variable x of f. Then you go like, but what if I need to refer to local variable x of main at this point for whatever reason? So you can actually do that because the debugger allows you, the first command that you want to know is frame. Yep, there we go. So frame is an actual command, and what it does is to show you quote unquote the call stack. So the way it works is it shows you that we are, oh darn it, it thinks that we are already in main because it thinks that we are already back to line 20, but we are not really quite back to line 20 yet. So it doesn't quite work the way that I wanted it to do, because it is the cursor is showing it is on line 14, but it really is already on line 20 because the frame already disappears with F, even though it still shows here. What am I going to do here? Okay, all right, let's stop the program, and then we'll have one more statement here. Okay, it's not useful, okay, but it gives me a chance to stop the program before it gets to the close brace here so that we can actually take a look at both frames. So that's what we're going to do next. Okay, same thing here. Then we go back to debug. All right, so run the code. It is now on this line, okay? So when you look at frame, okay, when you ask frame, we only have one frame at this point. Pound zero, frame zero, is always the frame that we are actually on in terms of the execution point. Okay, so the execution point is also where the green rectangle is circling. So we aren't in main right now. So that means we only have one single frame, which is also reflected in call stack over here. So when we single step into F, okay, then you can see that now we have two frames. One is F, one is main. And then when we single step through the line 13, now we are on line 14, and you say, okay, what is x? It says x is 42. That is correct. But also at the same time, when you ask frame, now it will give you two frames. Mm, it is not giving you two frames. Am I forgetting something about frame? Hmm. Okay, give me a second. Let me single step. What is x? X is 43. So, oh, frame only tells you the, no, it's not the current frame either. I know you can do a backtrace. There we go, backtrace. That's the command that I was looking for. Frame allows you to change the frame, but not to look at what frames are currently available. So backtrace, BT. So backtrace tells you that there are two frames right now. One frame, which is the current frame, is for function F, which is the active execution point. The other frame is pound one, which is main. So main it is still having its context available, but it's not quote unquote visible right now. Okay, so the command frame allows you to change it. So that means you can say frame one. So that would put the debugger into the frame of main, which means at this point, if you say print x, it will print 32 because it is looking at things from the perspective of main and not in F. But you can always say frame, frame with no command puts you back into the current frame, or it tells you what frame you're in at this point. So if you say frame 0, it will put you back into the frame in F, which in this case is going to give you 43 for local variable x. So this is pretty clear that we have two local variable x. One is, in main, the other one is in F. Yep. So the frame actually has a few things in it. The return address is one of the things. Local variables are also a part of the frame. And then later on, we'll also find out that parameters is also part of the frame. Yep. So a frame is a general term of the context in which a function knows how to get its stuff and know how to return to the caller. Are we doing okay so far? Okay. So one more thing I want to demonstrate before we move on to back to the assembly code. So now, because our current frame is in F, so we can ask, okay, what is the address of X? It gives you a bunch of numbers. I know it's hard for you guys to see. This is 9FC. But if you change the frame to the main, and then you ask the same thing, where is X? It will give you something that is different. This is A1C. So that is clear that variable X from main and local variable of F, they live at different places. There are two completely separate local variable X's. Is that okay? All right. So now we go back to the assembly code. Okay, so we'll go back to the assembly code to implement exactly the same program and then find out how this can be done. Okay, so I'm going to get back to this part here, and I'll just go ahead and write this code in assembly with only comments first. So we'll go ahead and copy and paste this code, copy, and then we go like cat2 local.ttp-asm, paste that code. We start with a no op instruction, and then the rest I'm going to comment out. So the beginning of each line is replaced by the two slashes. Okay, replace beginning with two slashes and a space. There we go. This is why I like VI, because you can do stuff like this. So we now look at function f. Okay, f is marked by an entry point f. Main is marked by an entry point main. Okay, so, and now the question is, what about the local variable x? So in this case, local variable x, now I will do it first, and then I'll explain what is going on here. So we'll go ahead and say, okay, x is a local variable of f, and this is a label. But the label is not telling me exactly where to find x. It is giving me an offset, okay? It is an offset of 0 from where the stack pointer points to by the time the stack or the frame is fully allocated. And then I have a LVS, which is local variable size, which is going to be f underscore x 1 plus. It is the number of bytes that we need for all the local variables. And in this case, this is just saying 1 byte. And then after that, we have the return address. Where do I find the return address? So that's going to be FLVS um, by itself or 1 plus. Yeah, that's a reverse Polish notation. It is the same as fx plus 1. Okay. The return address is really not needed. Okay. So we'll do it like this. And then main has the same thing. Okay. Main x is a label related to where to find local variable x, but it's just going to be a 0. And then main underscore LVS or local variable size is the offset to find the last local variable plus the size of the local variable itself. So because x is going to be a 1 byte unsigned integer, we'll just say 1 plus. And now we have to do something about the allocation and the deallocation of the local variables. So local variables, they live on the stack, which means you have to allocate, and when you're done, you have to deallocate. All right? So the way we allocate for all the local variables is to do something like this. LDI, I'm going to use B as a register, main LVS, And then we're going to decrease that much or subtract that much from the stack pointer. And then to deallocate, I go all the way to the end, until I'm ready to return, and I'm just going to add that back to the stack pointer. Okay, so it'll be more clear when we run the code inside when we look at the trace. Okay, so JMPI to main. So what we'll do is we're just going to do this part here. Okay, we'll just say, okay, we want to assign a value of 32 to wherever x is. So we'll only do this part. We won't even bother to call f at this point. Okay, we just want to look at it from main's perspective, just to understand how local variables are allocated and accessed. So now we are going to say LDI, pick a register. We can pick any register, A, B, or C. So I'm going to pick C in this case. Main X, add CD, and then LDI. We'll use register A with a 32. STCA. So we are not going to call F yet, okay? We're just performing this one single assignment statement here, and then we'll see how that works. Put a halt here. And then before we branch to main, we can also pretend to initialize the stack pointer by saying LDI D0. But we really don't need line 2 because when you reset the processor or when it starts, all registers start with a value of 0. Okay, so it's not really needed, but it's good to emphasize that if we do want to initialize the stack pointer, it is initialized to 0 because 0 is also 256, which is the location after the end at the end of the RAM space. All right, so we'll go ahead and run this code as it is. Okay, so we'll go to my repo folder, submit the program, so it will run. So there we go. And it's being recorded. Everything is being recorded, which means you can actually just write down the time so you can go back to a certain point of the lecture and then go like, okay, I need to re-examine that portion a little bit. All right, so this is the execution of the program, and we're going to take a look line by line, instruction by instruction, and figure out what each line is really doing. This line doesn't do anything useful, okay? It just needs to be here because of a certain bug in Logisim. No big deal. This line also doesn't need to be here. We just want to make sure that we initialize the stack pointer so that it starts at location 00, which is actually location 256. But because we decremented the stack pointer first, so this is the right location to be at when the stack is empty. And then we continue execution at the entry point of main because that's how programs execute, right? We start with main. So at this point, main is not even treated as a function for the most part. Okay, so we just have an entry point. So this is where things get a little bit more interesting. Is we load main LVS, which has a value of 1. Main LVS as a label is telling me the number of bytes that I need for all the local variables. So if you don't have any local variables, you can still have a main underscore LVS. You just define it to be 0, which is perfectly okay. There's nothing wrong with saying I do not need any local variables, because in that case, you're still subtracting, but you're subtracting 0 from the stack pointer, so the stack pointer is not changed because you don't have any local variables. But in this case, I do have one single byte of a local variable, so I'm changing the stack pointer from 00 to FF because of this subtraction instruction. So it is the same as 255 because FF is the hexadecimal version of 255. Okay, so the next instruction is this instruction here. It is loading not the address of local variable x, but the offset from where to find local variable x from where the stack pointer points to into register C. So because it is the only local variable, the stack pointer is already pointing at it. So that's why the offset is simply a 0, because the stack pointer is pointing to local variable x. But 0 is not the address, it is the offset. So in order to get the address, I have to add the stack pointer to the offset so it becomes the actual address. So at this point, okay, when we are done with line 24, register C actually has the address of local variable x in main. So at that point, I load 32, which is the value on the right-hand side of the assignment, to register A, and then I do a store, and that store is going to change location FF to 20, which is 32 in hexadecimal. That's how we store the value into the local variable. And at that point, we are done. And then these two instructions are really at the end of main in order to reclaim the space that were used for local variables. So these are all new concepts, okay? Well, or the concept of a local variable is new, but we can now see that local variables also live on the stack, okay? So I'll do one more thing, okay? I'm going to go back and, actually be nice and add more comments to the program or to the code, but the comment is not going to make any sense until you actually digest it, okay? Because otherwise they're really just comments, they're just text, so this is the number of bytes needed for local variables. This is how we allocate, okay? This is allocate space on stack for local variables. After this, C is the address of x minus the stack pointer. In other words, it is an offset from where the stack pointer points to where the local variable is supposed to be. Now, in this program, because we only have one single local variable, so it is not easy to see that, oh, okay, are they supposed to be the same thing or not? Well, they're not supposed to be the same thing all the time, but in this case, they are the same thing because that's the only thing we have on the stack. So now when we add the stack pointer back to register C becomes the address of x minus d, but because of the add here, it becomes d plus d. So when you use algebra, it becomes the address of x. And then at this point, a is not, a is just 32. There's no big deal to this one. So what are we actually storing here? We are dereferencing C, which means we are dereferencing the address of x in order to store the 32. But you can probably remember from CISP 360, the asterisk, which is the reference, and address of, they cancel out each other. So that means the actual operation we are performing here is simply x equals to 32, which is what the C code is calling for. Is that okay? And then the rest is really just deallocating. So this is also one, we are just loading the number of bytes needed, whoops, for local variables. And then we are now deallocating, okay, because whenever you add to the stack pointer, you're deallocating. So this is deallocating space on stack for local variables. Yep, it is almost the same as a push and a pop, except the push does not know what value to put into that location yet. And then the pop also does not care about the value by the time you pop. So the push is more like just allocating the space so that we have that space to do things with exactly. And then the pop is just deallocating because we don't, at that point, I don't really care what is stored at that location because I'm done with using that location as a local variable. Yep. Mm-hmm. Yep. Mm-hmm. X. Okay, so main X as a label is 0. because it was defined to be just 0. Because because the stack pointer points to the last thing that you allocate on the stack. And x being the only local variable is the last thing that you allocate from inside the function itself. Okay. Okay, so let's add another variable. Okay, so this is a good question. And what we'll do is we are changing the original code first. Okay, so we're going to go back to the C program and modify the C program first. And we'll just say that, okay, we have another local variable y. Okay, and now technically speaking, I probably should be pound including standard integer.h, and everywhere we use int, we have to specify that, we are using 8-bit integers, because otherwise the space that we allocate would not be correct, or it wouldn't match the C code. So technically speaking, this would be closer to what we really want are doing in assembly code, but it's more of a technicality in this program, because the range of the value that we are storing is okay with either type of integer. Okay, hmm? So the default, I do not know. Okay, if you want to know the default, this is the way they do it. So you just do a regular int, let's say z over here, and then you debug the code, and then you just run. I'm not sure whether it can do it without running the code. We can give it a try. So we can say size of z. Nope, it doesn't know it yet because it's not in the context yet. So we have to run the code or debug the code to that point. Okay, now that we are in here, we can ask the question again. So size of as an operator, yes, it is actually called an operator, tells you the number of bytes for a particular variable. So in this case, it's telling us that z as an int is a 4-byte or 32-bit integer. So that's quote unquote the default. Mm, billion, billion. Yeah, 32-bit would be -2 to +2 billion for signed, and then 0 to about 4 billion for unsigned. Well, I mean, how many people do we have on Earth? Way more than twice. Yeah, the world population is somewhere around 8 billion. So that means your 32-bit number is not that big. All right, so this is the C program. And now we want to look at the assembly code and see how we can adjust the assembly code to deal with this. So I'm going to adjust the actual code first. Okay, so now we have another integer y, and they're all 8-bit integers. Okay, so unless I say something about it, all integers are 8-bit wide, signed or unsigned. So now what do we do with the allocation here? So the label is the only part that needs to be changed. So we now go like, okay, where we can find y is where we can find x, but not exactly that, 1 byte after that. And then the total number of bytes we need for all the local variables would be the offset to find the last local variable plus 1. Okay, so now the rest of the program stays the same. It will still work. Okay, so let's just say that we want to make the program fancy, and now we want to say, what if we want to implement something like this? I want y to get the value of x. Let's make it even more complicated, plus 16. Okay, this is what I want to do. So how do we do this? When we look at an assignment operation, um, the problem with C, C++, and most other programming language is we read from left to right, but the operation of an assignment is right to left. In what sense, right? Because we don't really care about the left hand side until we evaluate the right hand side. So that's what I meant when I said, when we evaluate or when we execute an assignment operation, it is actually a right to left operation, because you first have to evaluate the right hand side, then you know the value that you need to store to the left-hand side. So I'm not even worrying about the left-hand side until I know what the right-hand side is. Is that okay? The right-hand side of the equal. Yep, because I first have to evaluate x plus 16. So in order to evaluate x plus 16, I need to get back to the value of x. So this is the way we do it. Okay, we can pick another register, let's say B, okay, main x. So you have to remember the label main x is really the offset to find x from where the stack pointer points to. So C would, or B in this case, would be the address of x, but we have to subtract the stack pointer from it, so that it becomes the offset from where the stack pointer points to the actual address of x. So everything is relative to the stack pointer now. Is that okay? Where we find x is relative to the stack pointer. Where we find y is relative to the stack pointer. The labels main x and main y, they are offset from where the stack pointer is pointing to. I can give you an example. Okay, let's just say that this class is doing a caravan and we decide to go to Burning Man together. Okay, and the ordering of the vehicles would always be the same. Okay, you know, I'm the first vehicle, and then you're the second vehicle, and you're the third vehicle, and so on. Okay, and then somebody forgot to bring toothbrush, and you have to order something from Amazon to deliver to in the middle of the desert in nowhere. Okay, you guys go like, how am I supposed to tell the Amazon truck where to deliver the stuff? And you go like, oh, but Tech has a GPS thing. He can broadcast his location, and Amazon, is smart enough to go like, okay, I can just go by your GPS location. As long as you stay put for 4 hours, we'll be able to find you. Okay, so now I become the stack pointer. I become the stack pointer because as we move, the location of me is always known. Okay, so the offset, which is main underscore x, main underscore y, and so on, is how many vehicles are you behind me in the caravan sequence. So you'll be the first vehicle behind me, you'll be the second vehicle behind me, third, fourth, and so on. So when you order something from Amazon, all you have to do is to go like, I am the third vehicle behind tax vehicle. But Amazon, using its crazy technology, knows exactly where to find me as long as I stay put for 4 hours. So now the delivery truck will say, okay, I have to go find Tack first. Okay, so the drone comes find me, and then they look up the address and go like, okay, but Tack is not the person who ordered this toothbrush. It is the third vehicle from Tack's vehicle. Okay, so they just count. Tack's vehicle is plus 0, plus 1, plus 2, plus 3. So now it knows exactly where to deliver that toothbrush. Is that okay? Is the analogy working okay? So it doesn't matter where we go, right? Because on one day I could be this at this part of the desert, and then the next day we are on our way back to Sacramento, and the whole caravan is somewhere else. But as long as we stay at that spot for more than 4 hours, some of you forget your toothpaste, okay, and you can order your toothpaste again from Amazon, even though the location has changed, okay, as long as Amazon knows where to find me, which is quote unquote the top of the stack, and it knows where you are relative to where I am, like the third vehicle, behind me. They can still deliver that toothpaste. Is that okay? Of course, in the desert, you don't need toothpaste because we got sand. And if you don't like the taste of sand, I'm sure you can find some cactus. Just break it apart, get the juice out, rub it into the sand, and that becomes your toothpaste. Hmm. Hmm? Yeah, that's it. That's the whole program. I mean, I'm not done yet. Okay, you know. Hmm? Oh, all the way to the top. Mm-hmm. Say that one more time. It's decremented, not incremented. The first time it decrements is here. Let me finish the program, and then when we run it, it'll be actually more visible from the trace itself. Because the program itself is kind of littered by commands and things that are spacing out everything. So so we have a add BD. So the idea of add BD is B is now what it used to be plus D, but minus D plus D cancels out. So that means it really is just the address of X. So register B now has the value of the address of X. And that means I need to dereference it once, okay? Because in this case, B is going to be the dereference of the address of X, which is really just the value of X. And then after that, I need to add 16 to it. So I have to load A with whatever the value I need to add, and then we can just perform the add here. So at this point, B is going to be X plus 16. And now we focus, so we are now done on the right-hand side of the assignment. We can now focus on the left-hand side. So the left-hand side is just, y needs to store the value. So we need to find out where y is supposed to be. Um, on the caravan, y is this many bytes behind the lead vehicle. So C is the address of y minus the stack pointer. So that's why we always have to add the stack pointer to the offset, because otherwise you're not getting the address, you're just getting the offset. You're not getting the address, you're getting only the offset. So now we have the address, and the ST instruction will now finish the entire operation. B contains the value of the right hand side. So now we just store the value of B to wherever C is pointing to, because C is the address of Y. So when you dereference register C, you get to the content of Y. So let me just comment this. Y is now X plus 16. Okay. So this is the code, and we're going to test run it. So before we test run it, it is good to have a mental picture of where X is supposed to be on the stack in memory space and where Y is supposed to be in memory space. Drawing a picture can be helpful, okay? So when you look at the top of RAM, this is location 255, this is location 254, and so on. The stack pointer used to point to one location above the top of everything. So when in this case, because we have 2 bytes that we need for local variables, so that means the stack pointer is going to point here after the allocation because it's subtracting twice. Okay, it's you're subtracting 2 from the stack pointer to allocate for those 2 bytes. X as an offset of 0. So X is actually here, right at where the stack pointer points to. It is vehicle 1 or 0 of the caravan. Y is 1 after that. Is that okay? Yes. Yep. All the concepts that we are learning are stacking up to. Yes. Yes. Mm-hmm. Yep. All right. So now when we store, so according to the program that we were running, we are putting a value into X first, and then Y is 16 plus that value, right? So I cannot remember the values anymore. I think it's 32 and 16. So that means X should be storing a 20 this time, and then Y should be storing a 30 because 20 in hexadecimal plus 16, which is 10 in hexadecimal, should be 30. Okay, so now we go back to the trace, okay, and then we try to take a look and see if that's exactly what happened. So I'm skipping all the way to the end here. Okay, location FF, which is location 255, is getting a 30. That's all good. And then location FE is getting a value of 20, which is also what we anticipated. Are we good so far? Okay. So now we can look into parameters. Okay. Parameters are kind of like local variables, except they are allocated and initialized by the caller in the reverse order. Okay. So we are going to take a look at a program that we are not going to run yet. Okay. So are we good with not keeping this program? Can I erase it? We good? Okay. So I'm going to erase this program, and I will still do a pound include stdint standard integer.h just so that I can use the types. uint8 underscore t, and we're just going to call this sum because that's all it's going to do. It has local variable x or parameter x. It has parameter y. Okay, misspelled here. uint 8 underscore tx, uint 8 underscore ty, and it's going to return x plus y. And then this is main, int main. And in main, we have a local variable. I can call it x or y, but let's call it z. Z is the sum of 2 and 3, and then we have a return 0. Okay, so this time the focus is no longer the local variable z in main. Now the question is, what about those parameters x and y? So how do we pass parameters to a function? You really don't have a whole lot of ways to do it. Okay, there are three main ways to do it. One is to use registers. Okay, so you just have the standard or the agreement. The first parameter is in register A, the second parameter is in register B, and so on. How many registers do we have? We only have four, but register D is already used as a stack pointer. So we only got three. So that means any function that needs more than three parameters, you cannot implement. That doesn't sound, reasonable to me. So, okay, this approach doesn't work. Two, you can use static locations. Okay, you can designate this location in RAM is parameter x of sum. Okay, we have a problem with that too, because now you cannot do recursion. Okay, so the only way to fix the problem where you don't have a limitation per se, and you can also do recursion, is to use the stack again. Okay, so now the question is, how do we use the stack to do this? So we're gonna take this code and then write the assembly version of this, and along the way I will explain the concepts. So over here we're gonna do about the same thing. Okay, so cat to params.ttpasm, paste like so, and now we can edit that program. Okay. All right, start with no op. And for now, we will just JMPI to main, and the main is over here. We'll put a halt at the end. And also, this is the entry point of main. This is the entry point of sum. So we'll handle the caller first. Okay, so we'll handle main first. So this part is the same as before. This is the first and only local variable. It has an offset of 0 from the stack pointer after the local variable space is allocated. LVS, the total number of bytes that we need. You can type a 1 over here, but I prefer to be more relative, which is the offset to find the last local variable plus the size of the last local variable. This way I can add more local variables, in a more flexible way. Okay, so that's just me, but if you don't like this approach, you can always just say 1. All right. But main underscore Z and main underscore LVS, those are just labels. All they do on line 11 and 12 is to tell the assembler every time you see main underscore Z, it means 0. Every time you see main underscore LVS, it means 1. That is all those two lines are going to do. Are they actually going to do anything about the stack pointer? No. Okay, line 11 and line 12, they do not do a single thing to the stack pointer itself at runtime. So that is why we need to use mnemonics to do that. So we're going to use this and go like, okay, the total number of bytes that we need on the stack is now in register B, and then just subtract that much from register D for allocation purposes. And then when we want to deallocate, it's kind of the same thing, except we increase the stack pointer by that much. Okay, so now we go back into this code, okay, and we want to call sum at this point. So calling sum, we know a part of it, but we don't know the other part of it. So we know the part where we have to push the return address, right? So we have to specify return address, and since this is the only one, we can just call it return address one. It's a label. So we have to put it into a register first, say register A, okay, and like so. And then we decrement the stack pointer, and then we do stda. So these three instructions together is for pushing the return address on the stack so that the subroutine knows where to go back to. But after we push the return address on the stack, we still need a JMPI to the entry point of the function that we're calling to continue execution where the function is. So this part is something from the past. Okay, we talked about this in just calling and returning. Okay, so this part is okay. It has nothing to do with parameters. So whatever we need to do about parameters has to be done before this. Okay, so we go like, okay, so how do we get the parameters on the stack? In other words, the first thing we need to do is to push the two parameters. But now you have a question, which is, should we push the 3 first or should we push the 2 first? Okay, because you have a choice of the ordering. Okay, but you don't really have a choice because the C standard says you always push the last argument first. Okay, so our last argument is a 3, so we need to push 3 first on the stack, and then we push the 2 on the stack. Okay, how do we push 3 on the stack? Kind of the same thing that we do when we push the return address, except we're not pushing the return address. We're just pushing a value of 3. So you put 3 into register A, we decrement the stack pointer, and then we store the whatever is in A, which is 3, into wherever the stack pointer is pointing to. And then the same thing over here, LDI, register A is fine, to decrement D, std A, so these two would push the two parameters on the stack, and whatever the following code is going to push the return address on the stack. So that's how it looks like from the caller's perspective. There's one more thing that is really important. By the time we get back from the callee, guess what is still on the stack? The parameters are still on the stack. The return address is not on the stack anymore because according to the caller-callee agreement, it is the job of the callee to pop the return address. So we know the return address will be gone, but we push 3 things on the stack, the return address being the last thing that we push. So the first 2 things that we push on the stack would be the 3 and the 2. They are still sitting on the stack. But at this point, they are not useful anymore because the whole function is done. So why do you keep the arguments for calling a function when a function is all done already? We don't need that, right? So that means we have to deallocate those 2 bytes and get them back by incrementing the stack pointer twice. Okay, the first increment D reclaims the space that was used for the 2. The second increment D reclaims the space that was used by the 3 on the stack. Are we good so far? Yep. Huh? Set set whose value to something else. The stack pointer. The stack pointer is nothing more than a bookmark. So this is just saying, okay, these 2 pages are not useful to me anymore. The bookmark is really saying, if I need another page, which page can I use? Yes, if I need it. If I need it, right? Yep. The value is still there. Yes, later on. Yep. Okay, so what we'll do is we're going to run this code with only one little thing here. Okay, so we'll still do the initialization of the stack pointer, no big deal. And we'll just put a halt instruction here. In other words, this program is not going to finish. Okay, we are going to stop right at the entry point of sum because we want to know what the stack looks like when we get to that point so that we know how to retrieve x and y from the perspective of sum. Are we good so far? Okay, so this program is not done, okay, but it is done to the point where we can now have a picture of what the stack looks like from the perspective of the called function. All right, so that's what we're going to do. We're going to run it, okay, so submit this whole thing. Why is it taking so long? Oh, okay, just as I complain. All right, there we go. And did it complete correctly? Yes. Okay. So now we go back to the assembler, go back to the trace. So now we go kind of line by line again, okay? Um, Nothing to really talk about here. Initialization of the stack pointer, continuing at the entry point of main. Inside main, we have to first allocate for the local variable space. There's only one, okay? So B only gets a value of one. Decrement one from the stack pointer, the stack pointer becomes FF or 255. So that's where main X is supposed to be. Okay. So if you want to draw a picture, and I strongly recommend people to use a pictorial representation, you can either use a picture or you can use a spreadsheet. So I'm going to use a spreadsheet here. Okay. So I go to the CIS 310 folder. Okay. Maybe go to the shared folder. Okay, anything in the share folder you can view. Okay, that's all read access to all of you. So I'm going to create a new spreadsheet by today's date. So this way it's easy for you to find the spreadsheet when you watch the video. So it's today is 25, 10, 27. There we go. So what I'm going to do is I'm going to use 255, 254, 255, 253, sorry. I will do the more systematic way. This is more systematic, like so. So in this program, okay, this is where x of main is. So x of main is supposed to be here. And then what do we push after that? So after that, we push the 3, then we push the 2, and then we push the return address. So that is what the stack looks like. So by the time we get to the function, D is pointing here. This is the picture when we're at the entry point of sum. Is that okay? So now we want to see if that really is the case when we look at the trace. So when we look at the trace over here, okay, we are still constructing stuff, right? So A gets a value of 3, and then we decrement the stack pointer and use location FE to store the 3, which is location 254. So we now double check to make sure that that is exactly what we're doing. Okay, cool. So now we go back to the trace again. And then this time we put a 2 into register A, and then we decrement the stack pointer, and then store A to where the stack pointer is, which is essentially, no, I take it back. Actually, we are here. This is 2, okay, so we are now pushing the 2, register A, get a value of 2 because of LDI A2. We decrement the stack pointer, so the stack pointer is now pointing to location 253 in decimal or FD in hexadecimal, and then we store the 2 at that location. So we double check. Aha, this is where the 2 is supposed to be. And then the last item that we push on the stack is the return address. So we double check too. Okay, so we go back here and we say, okay, load the label return address 1, which turns out to be 17. Decrement the stack pointer. So this is the next available location, which is location 252. And then we store that at that location. So now we switch back to the stack. and go like, oh, okay, that's exactly where it is going. Are we good so far? So that means the frame from the perspective of sum would be these 3 bytes. That is the frame of sum. It consists of the return address and the 2 parameters that it has. Are we doing okay so far? Okay. So now from the perspective of sum, we also want to know where to find stuff, right? So from the perspective of sum, the offset to the return address, offset to, okay, so offset to return address is 0 at the entry point. The offset to the first parameter, which is x, is 1. The offset to the second parameter is 2. Is that making any sense? It does not have local variables because if it did have local variables, then we would have chewed up additional locations, but it does not. Mm-hmm. Yep. The stack pointer. The stack pointer is already pointing to this location. So if we need to access X, it'll be just 1 byte after where the stack pointer points to. If we need to access Y, it'll be 2 bytes after where the stack pointer points to. So all of these offsets are in terms of from the perspective of the stack pointer, offset from where the stack pointer points to. Are we good so far? Yes. Yep. So given this picture, I can now go back to my code here, okay? And I can now define some additional stuff for sum itself. So I can now say some return address is 0, okay? Because the offset from where the stack pointer points to, in order for me to get the return address, would be an offset of 0, because that's exactly where the stack pointer points to. And then we can say sum underscore x is going to be some return address 1 plus because it's 1 byte after that. And then sum underscore y is going to be sum underscore x 1 plus because that's also 1 byte after that. Are we doing okay so far with the label definition? So the 3 lines of label definitions from line 7 to line 9 is really just a symbolic way so that it's easier for me to refer to, oh, I need to get to x. Where is x? Where do I find x relative to where the stack pointer points to? Okay. Now, if I have perfect memory and I can keep track of everything in my head, I don't need the labels. But I don't. I cannot do that, right? I cannot remember all those things. So that's why I need labels to help me remember where I can find the various items on the stack from the perspective as an offset from where the stack pointer points to. All right, so now we can go back to the code here and go like, okay, so let's take out a halt instruction and actually try to do the implementation. So the first thing is I need to get back to the value of x. Okay, so we'll do a LDI, let's use b and sum underscore x. So at this point, B is going to be the address of X as a parameter minus D because it is just an offset from where the stack pointer points to where I can actually find local variable, parameter X. So that means to get to the address, I have to add back the stack pointer. So I have to add BD so that b becomes the address of x minus d, the offset, plus d, which is basically what I do here. So in the end, what it really is b is now the address of x. But I'm not adding the address of x to the address of y. I'm trying to add the value of x to the value of y. So that means I need another LD here to dereference it. So B is now the dereference of what it used to be, which is the address of x, which means, oh, okay, at this point, B is really just the value of x. Is that okay? All right. And we're going to do about the same thing with y, okay? Except for y, I'm going to use register A, okay? Yeah, underscore. There we go. LDAA. So now that I have register A being the value of y, Now I can just add those two, right? I can add AB, and now register A becomes the sum. Okay, so now register A is X plus Y. So are we good up to this point? Okay. So let's just say that you guys go like, no, I'm not good up to this point. I don't know what is happening here. Well, this is why the trace is helpful. Okay, because if you don't know what is happening up to a certain point, just put a halt instruction. Okay, halt right here. Okay, remember to save the code first, and then just run it. Okay, so we're gonna run it and find out what is going on. How are we calculating the address of X and the address of Y, and how do we get to the value based on the address? Blah blah blah. Everything is here. Okay, so before that, I have to go back to the code because I need to find out which lines we are at because we explained the portion already. So this is line 10. Okay, very good. So we go back to the trace and say, okay, we only need to continue the discussion from line 10, which is here. So on line 10, B gets a value of 0, 1, and then we add the stack pointer to it, it becomes FD. So the question is that where we're supposed to find parameter X? Is it at location FD? I really cannot remember. So we go back to the picture and go like, okay, what is at location FD, which is 253? Oh, it really is X. Cool. And then we go back to the trace again and go like, okay, in addition to X, I also need to find Y. So this is the offset to Y. After this, we have the address of Y. And then after this, we're supposed to have the value of Y. So we are going like, okay, is it actually at location FE, which is 254? Yes. So now the next question is, are we getting 2 into the right register? So we can now see that register A ends up with a value of 3. Register, oh, this is after the adding. Let's see. This is B, this is A, and this is the result. So register B gets the value of X. Is it supposed to be 2? Well, let's double check. Yep, X is supposed to be 2. And then register A is supposed to get the value of Y. Is it supposed to be 3? Yep, Y is supposed to have a value of 3. And then when we add those two, we get the value of 5. So now we are done with the expression of the return statement. Okay, so what is left to do? Well, we just need to use the return address to go back to the caller, right? So we'll go ahead and do that. Okay, take out the halt instruction here. And then we just go like, yeah, we're ready to go back. Yes, I know it sounds like I'm forgetting something, but wait and see. So we go like, okay, let's pop, right? So pop means you retrieve the content of where the stack pointer points to first, and then you increment the stack pointer after to deallocate the location. And then register B now contains the return address, which means, oh, all I need to do is to do a JMPB right here to continue execution. Then you guys are going like, but Tech, aren't you forgetting something about what to do with register A? Because we're supposed to return the value of register A as the return value. Okay, so it would appear that I have forgotten something. Well, actually, I did not forget because the agreement between the caller and the callee, so this is a key document to read. Okay, it is very, very important. So on here, we can say, okay, from the callee side, okay, we want to know how to specify the return value. So we can now say, at the exit point of the callee, if the callee has a scalar return value, use register A to store the return value. So let me just highlight the portion that is important here. Okay, so we look at this and go like, I can understand every single word, but exactly what does scalar mean in the context of a return value? Okay, so when you encounter this question, what do you do? ChatGPT or Gemini, take your pick. Okay, nope. Okay, so we'll ask Gemini, but so whenever you use an AI tool like this, um, you have to be specific. Okay, give it the correct context first, because scalar has many different meanings in different contexts. So you have to give it the right context. So you can now say, in the context of a return value in C++, what does scalar mean? Okay, so because a lot of people just ask, what is scalar? Well, it doesn't have the right context to tell you what scalar means in that case. And guess what? Most AI or GPTs do not say, well, scalar has different meanings in different contexts. Which context are you referring to? It doesn't ask you that question. It makes an assumption and just go with it. Okay? So that's why you have to be very clear. Okay? In this context, what does it mean? And probably I should have used the simpler model, but it's okay. It'll just burn a few more bottles of water. All right, so in C++, a scalar type is one that holds a single value. This includes blah, 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 blah. Okay, so do you think an 8-bit unsigned integer is one of those? Well, let's say you're not sure, okay? Let's just say you're not sure. Okay, you can now ask, so is u in a underscore t considered a scalar type in this context? Because it's not shown here, right? It was not explicitly shown. So you can double check and confirm it. So if you ask, yes, absolutely. So there you go. Okay, so there are ways to use AI and then there are ways not to use AI, but I would say this is a pretty good application of AI. Okay, cool. All right, so nice. So now we go back to the document that we were just talking about, which is, I think it's this one. Okay, they're both the same documents at different points. So now we go like, oh, okay, so if the sum is already in register A, then we are done. Okay, the return value is already specified. Is that okay? All right. So we have a few more things to do because right now we are done on the from the perspective of the callee. So we have to finish up what the caller is supposed to do about the return value. So now we go back to the caller side and go like, okay, we are not quite done with the whole thing yet because we are supposed to store the return value to local variable z of main. So this is where we continue the code over here. But you can always put a halt instruction here, which means you can now say, are we sure that register A at the halt instruction of line 48, are we having 5 in register A? You can confirm that. Okay. You can also confirm we are supposed to have deallocated everything on the stack. So is the stack pointer back to location 0? And you can look at the trace and confirm that too. Okay. So I'm not going to do that because I'm fairly convinced that that is the case, but I can still say register A is now um, the result of calling sum with 2 and 3 as its parameters. So now all I need to do is to say, okay, where are you z? Okay, where am I supposed to store the result? So it's a pretty standard thing now, okay? Main underscore z is the offset. Now it is the address. We just need to stash whatever register A has, which is the return value, to wherever register B is pointing to, because register B now has the address of Z. And that should conclude the whole thing. So that means in the trace or in the picture that we have looked at earlier, that should put a 5 to this location. Okay, so we'll see whether that actually works the way it's supposed to or not. But this is the important part. The important part is before you test run the code, you have to know what it is supposed to do. Okay, so I have an idea of what it is supposed to do, but now I'm going to run the code to see if it is consistent. If it is consistent, great. If it is not consistent, even better, because then I'm going to learn something new. So we'll see. We'll see. Huh? Yeah, every mistake is a learning opportunity. Making mistakes is only a bad thing when people make exactly the same mistake because they did exactly the same thing 10 times in a row. That would not be good. But if you make 10 different mistakes every single time and you figure out why you make that mistake or what it is about every single time, you just got 10 free lessons in life. Now, I'm not counting life-changing mistakes, so those you have to be careful about. So don't try to drive your car at 140 miles per hour on the highway. Ignore all the stoplights and the red lights. Don't do that, okay? Those are not the kind of mistakes that I'm talking about. So all I'm doing is checking that we did store a 5 to location FF, which is location 255, which is exactly where X is supposed to be. So now it's all good. All good. Yes. Yep. But if you look closer at the trace, you can actually see those two increments too. So this is the first increment. So when this is the last line in the callee, and this is back to the caller. So when we get back to the caller, the stack pointer went from FD to FE first, and it went from FE back to FF. And then at the very end of the program, when after we deallocate the local variable, the stack pointer went all the way back to 0, 0, which means the stack becomes empty again. We don't have anything on the stack at that point. All right. So are there any questions? So I may not be able to maintain this snapshot all the time, okay, but now would be a good time to take a snapshot if you want to. But you can also use the tool. So this is probably a good time to talk about the tool itself. So if you want to use a Reefer Spider the same way that I do in this class, you can go to TTP ASM tools and techniques, okay? And that would be in tracing TTP ASM code execution. So this is a document that gives you all the instructions of how to do all that stuff. Um, so the longer way is it's doable, okay? It's just not the best way to do it, okay? You just end up doing a lot of work every single time. So I do not recommend it, but you can still do it. The shorter way is to use the tool that I have already prepared so that you can do it in Windows. It also works in Mac OS and also Linux. But the process of doing this is a little bit involved, okay? So if you think that you will eventually use River Spider, which I highly recommend because that's the best tool you can use to debug your programs later on, you might want to get that process started now, okay? Just in case it doesn't work the first time, you can bring your computer here and I can take a look. hmm Okay, that's a good question. We have about 5 more minutes, so we can actually do something like that. Okay, so this time we'll take a look at a. Mhm. So River Spider relies on Google Sheets, so you have to configure the Google Sheet first. There are instructions of how to configure the Google Sheet. The River Spider package actually has its own README file, so you can read that first. Okay, so we are going to take a look at this particular thing. Okay, so we'll just write the code in C first. Okay, so uint8 underscore t post increment and uint8 underscore t, and this time we have a pointer to an integer. Okay, ptr. It's right there. It has a local variable. Okay, your old value. And then the first thing we do, this is not the best way to do it, but as an illustration of how we do this, this is one way to do it. So now we say whatever PTR is pointing to, okay, is incremented by 1. So we're not incrementing the pointer, we're incrementing whatever is at the pointer. And then we just return old value. Okay. All right. So this is the function that we are implementing, and I'm not going to even call that, okay, because we may not have enough time to finish the calling, but I can at least show you what the stack would look like. Okay. So from the perspective of the stack, old value is right at where the stack pointer points to. Okay. So old value, or I should say post inc old value, is where the stack pointer points to. That's because it is the first and only local variables. So the allocation, if you look at how the stack allocates things, so if you look at it as a picture, PTR as a parameter is at the highest portion of the frame. The second thing is going to be the return address because the return address is pushed after the pointer, after the argument. And then the last thing on the stack is what the function itself has to allocate, which is old value. So that means this is at exactly where the stack pointer points to, or I can say the stack pointer plus 0. This is 1 byte off, and this is 2 bytes off. Okay, so now we can say post inc. So the way I like to do it is I use LVS to track the number of bytes I need for all the local variables. So even though in this case we only have one single local variable and it only takes 1 byte, I still like the same method. Okay, I like consistency so that I do things exactly the same way for exactly the same reason. Um, okay, so we have now post inc. So LVS is also exactly where we find return address, but typically you don't need to find the return address because by the time we need return address, the stack pointer will be pointing at it already. So the only thing I also need to find is the pointer. So the pointer is post inc underscore LVS 1 plus. So that's how I figure out all the offsets. So when we get to the actual body of the function, the first thing we need to do is to allocate for the local variables. Because this thing here, old value, is not set up by the caller. It has to be set up by the callee itself. So it has to be the first thing to do. So we have the LDIB with post inc underscore LVS. And then you just have to subtract that from the stack pointer. And then the way I do it is I always finish do this first because before I forget. And then the return here is LDIB or LDB with D, increment D, JMPB. So that's really just the return. So I always do this first, and then before I go back to backfill the body of the thing. So when we backfill, the first thing we need to do is to get whatever pointer points to and then store that to old value. Okay, so we can do that. Um, post inc PTR, that's the offset. This is the address. And then we need two dereferences this time. The first dereference get PTR itself, the parameter. The second one dereferences the parameter. So we need two. So now B is the right-hand side of line 3, and now we just need to compute the address of the left-hand side, LDIA, post inc underscore old value, add AD, and then we just need a STAB. So that would finish line 3. So now we can go to line 4. So because I did not do something smart to save it first, so I need to do the whole thing again. Okay, LDIB with post inc PTR, add BD. So this is the address of PTR, and I need to do another BD to get to PTR itself. Now I have to be careful because register B is PTR itself. I need to get what it points to without destroying register B itself. So now I get to whatever value it points to, increment the value that it points to, and then store it back to where PTR is pointing to. So this sequence of instructions would implement um, line 4. And then finally, we just need to return old value. So that is relatively simple, okay? Because in that case, we just have to do LDIA with post inc underscore old value, add AD to get to the address of old value, and then do LDAA so that I get to the value of the variable old value. And because register A is where the return value is supposed to go, so this will finish the whole thing. So is that helping? Mm, no. So the caller never really needs to know the offsets. So from the caller's perspective, you just look at the list of arguments, push the arguments in the reverse order, push the return address on the stack, go to the subroutine, go to the function, and then when it comes back, deallocate your arguments. That's all you need to do from the caller's perspective. Yes. So that's up to the callee to determine. Yeah. So the caller never needs to know how the callee needs to use its frame. The caller just goes like, okay, I have this list of arguments. I will push the arguments in the reverse order. Then I push the return address. Then I go do a JMPI to the entry point of the function. When the function returns, you just clean up all the arguments. And from the caller's perspective, that's all you need to do. Well, okay, so this is what we can do on Wednesday. So you create a sample program that you think illustrates what you want to find out, and then you compile that in C, make sure it works syntactically and semantically, and then I'll do it in assembly. Is that okay? And this is also for the rest of the class too. I mean, if you guys want me to demonstrate a particular concept that relates to what we have been talking about, and it's a little difficult for you to convey what you want me to explain, you can always just give me a sample program to implement in assembly, and then I can just use the implementation itself to explain the concept. All right. So we are done with the lecture portion. Unfortunately, we are out of time. So we are going to work on the lab today. So the lab today is this one, which is params and return value, which is exactly what we did in class. So we'll, hmm? Did we? Oh, we didn't do the stack operation? Yeah. Okay, well, we'll do the stack operation then. The stack operation one, oh, do you mean this one? Uh, okay, gotcha. All right, let's do this one then. Thank you. So this is 27th. Hmm? It was marked what? Oh, because I changed it. Yes, I remember. All right, save. I think that's it. Cool. All right. So remember this one, you only got 3 attempts. Because people are used to, infinite number of approaches, and the access code is LIFO, LIFO, all in lowercase. All right, I'm gonna stop the recorder, try to get it up.